Welcome to this problem walkthrough. Today, we'll be exploring problem number 1236, titled Web Crawler. This problem challenges us to design an efficient algorithm for navigating through interconnected web pages. Let's dive in and explore the approaches we can take to solve it. In this problem, you're tasked with implementing a web crawler. The crawler begins at a given URL, called Start URL, and uses a provided HTML parser interface to explore the web. The goal is to visit all pages that share the same hostname as the start URL while ensuring that no URL is visited more than once. The crawler will return a list of all the URLs it visited, sorted in lexicographical order. The function you'll implement is called crawl, and it takes two parameters, the start URL, which is the initial URL, and HTML parser, which is an object that provides a method for extracting all URLs from the content of a given page. This is the foundation of the task, crawling through web pages, collecting URLs, and ensuring they meet the specified criteria. The output of your function is expected to be a sorted list of all the distinct URLs visited during the crawl. Let's look at an example to make this more concrete. Suppose the starting URL is http://news.yahoo.com/news. When you call HTML parser.getURLs on this page, it returns three URLs, http://news.yahoo.com/news, http://news.yahoo.com/news/topics, and http://news.yahoo.com/us. Then, the crawler visits http://news.yahoo.com/news/topics, and that page returns two URLs, both of which have already been visited. Finally, visiting http://news.yahoo.com/us reveals another URL, but it too has already been crawled. By the end of this process, the crawler has visited three unique pages. The output for the previous example would be a list of the three distinct URLs visited, sorted in lexicographical order, http://news.yahoo.com/news, http://news.yahoo.com/news/topics, and http://news.yahoo.com/us. The explanation highlights the sequence of events, starting at the initial URL, extracting links, and avoiding revisiting duplicates. For instance, when the crawler processes http://news.yahoo.com/news/topics, it ignores URLs that were already visited. Similarly, when crawling http://news.yahoo.com/us, no new links are added since they are duplicates. This ensures efficiency and correctness in the final output. A second example illustrates similar behavior, starting with http://example.com/a. Here, the crawler discovers two new URLs, http://example.com/b and http://example.com/c, and processes them while avoiding duplicates. The final output is again a sorted list of the unique URLs visited. In the second example, the output contains three URLs, http://example.com/a, http://example.com/b, and http://example.com/c, sorted in lexicographical order. The explanation outlines the steps clearly, starting at http://example.com/a, extracting two new links, and then visiting those pages. When the crawler reaches http://example.com/b, it finds links that have already been visited, so those are ignored. Finally, http://example.com/c is processed, but no additional URLs are found. This ensures that only distinct URLs are included in the result. The problem also specifies constraints to keep in mind while implementing the solution. For example, the number of URLs can be as large as 10,000, and you need to extract the hostname from each URL to determine if it matches the start URL's hostname. The implementation must handle these details correctly to produce the expected output. There are several edge cases and scenarios to account for while solving this problem. First, if there's only one URL available, the crawler should simply return it. For URLs with different hostnames, the crawler must ensure they are ignored and only process those matching the start URL hostname. Circular references, where pages link back to previously visited ones, must be handled carefully to avoid infinite loops. Similarly, empty pages that return no links should not disrupt the crawling process. Other URLs still need to be processed. Finally, given the potential scale of up to 10,000 URLs, the solution must be efficient, ensuring no duplicates and maintaining lexicographical order in the results. These considerations are critical for building a robust and reliable web crawler. To solve the web crawler problem, we first considered a brute force approach. The idea here is straightforward: crawl every URL encountered starting from the given start URL, without applying any filters. This could be done using a breadth-first search, where we use a queue to explore each page layer by layer, marking pages as visited to avoid revisiting them. However, this approach has a critical flaw: it ignores the requirement to restrict crawling to URLs that share the same hostname as the start URL. As a result, it wastes resources by crawling irrelevant domains and performing unnecessary work. While the time complexity of this approach is O, V plus E, with V representing the total number of pages and E the total number of links, it ultimately fails to meet the problem's constraints and is therefore not a viable solution. A more effective solution is the optimized approach, which uses breadth-first search while applying hostname filtering. The intuition here is to ensure that we only crawl pages that belong to the same hostname as the start URL. This is achieved by leveraging the URLparse library in Python to extract the hostname of URLs. The process begins by parsing the hostname of the start URL and initializing a queue to manage the breadth-first traversal. We also maintain a set of visited URLs to avoid redundant crawling. As we process each URL using HTML parser.getURLs, we check whether the hostname matches the one from start URL. If it does, we add the URL to the queue and mark it as visited. This approach efficiently filters out irrelevant domains and ensures that only valid pages are explored. The key insight here is that extracting and comparing hostnames not only simplifies the logic but also ensures that we meet the problem's requirements. The algorithm systematically handles this by parsing the hostname, maintaining a queue and visited set, and performing BFS until all pages with the same hostname are crawled. The complexity of this optimized approach is O, V plus E, where V represents the number of pages within the same hostname and E represents the total number of valid links between these pages. This makes it efficient while adhering to the problem's constraints. Ultimately, we chose this strategy, optimized BFS with hostname filtering, because it provides a clear balance of correctness, efficiency, and adherence to the requirements. Unlike the brute force approach, which is simpler but fails to respect the hostname constraint, this method is slightly more complex but avoids redundant work and ensures we only crawl the necessary pages. By exploring the web graph layer by layer, it guarantees correctness while maintaining clarity and efficiency, making it the ideal solution for this problem. To solve the problem of crawling all URLs starting from a given page, we need to ensure that our approach systematically explores all links while avoiding revisiting the same URLs. This is achieved using two critical data structures, a queue and a set. The queue is used to store URLs that are yet to be processed, maintaining the breadth-first search order. This ensures that we traverse URLs level by level, which is ideal for web crawling. On the other hand, the set helps us track already visited URLs, allowing us to efficiently check whether a URL has been processed. This prevents infinite loops, which could occur due to cyclic links. Together, these structures allow us to maintain both order and efficiency during the crawl. The process begins by adding the starting URL to the queue as the first page to explore. At the same time, it is added to the visited set to ensure we don't revisit it, setting the foundation for our algorithm. Now that we've initialized our data structures and added the starting URL, we proceed with the iterative part of the algorithm. While the queue is not empty, we repeatedly remove the front URL for processing. This URL represents the current page we are analyzing. Using an HTML parsing tool such as Beautiful Soup in Python, we extract all outgoing links from this page. These are the URLs that the current page links to. For each of these links, we check whether it has already been visited. If not, we enqueue it into the queue for future processing and add it to the visited set to ensure it is not processed again. This avoids redundant work and prevents infinite loops caused by cyclic links. Additionally, edge cases must be handled carefully. For instance, malformed or unreachable URLs should be skipped to avoid unnecessary errors. Cyclic links are naturally handled by the visited set, while memory usage becomes a potential concern when crawling very large websites. For such scenarios, optimization techniques like periodically saving visited URLs to disk can help manage resource constraints. There are a few important insights to consider when analyzing this approach. First, the choice of BFS over DFS is deliberate. BFS systematically explores all URLs at the same depth before diving deeper into the graph, which is particularly beneficial for applications like search engine indexing. Second, the use of a visited set is crucial for avoiding cycles. Without it, the algorithm could get stuck processing the same URLs repeatedly, wasting resources. Finally, while this brute force method works well for small to medium websites, it may face challenges with scalability when dealing with larger sites. Optimizations like filtering URLs by hostname or limiting the depth of the crawl can help address this. Regarding the data structures, the queue is essential for maintaining BFS order by allowing us to append new URLs and remove the front URL for processing, while the set provides an efficient way to track and check visited URLs. Together, they form the backbone of this algorithm. To evaluate the efficiency of our algorithm, let's analyze its complexity. For time complexity, fetching outgoing links for a single page takes O(m), where m is the number of links on that page. Checking if a URL is in the visited set has an average time complexity of O(1). Thus, for n pages crawled, the total time complexity is O(n*m), where n is the number of pages and m is the average number of outgoing links per page. For space complexity, the queue requires O(n) space to store pages to be crawled, and the visited set also takes O(n) space to store all processed URLs. Therefore, the combined space complexity is O(n). This analysis highlights that while the algorithm is efficient for small to medium websites, memory usage and processing time can grow significantly for larger websites, underlining the importance of potential optimizations in such cases. Here, we are implementing a web crawler using a breadth-first search approach. First, we define a crawl method that takes in the starting URL and an HTML parser, which is an interface to fetch URLs from a given page. To begin, we extract the hostname from the start URL using a helper method called get_hostname. This is important because we only want to crawl pages that belong to the same domain as the starting URL. Next, we initialize a set called visited to keep track of URLs we've already processed, ensuring we don't revisit them, and a queue using Python's deque for managing our BFS traversal. We add the start URL to both the visited set and the queue. Then, we enter a while loop that runs as long as there are URLs in the queue. Inside the loop, we dequeue a URL for processing and use the HTML parser.getURLs method to fetch all the URLs linked from the current page. For each of these fetched URLs, we check two conditions: whether the URL has not been visited yet and whether it belongs to the same hostname as the starting URL. If both conditions are satisfied, we add the URL to the visited set and enqueue it for further traversal. Finally, once the queue is empty, meaning all reachable pages have been processed, we return the visited URLs as a list. To support the functionality described earlier, we define the get_hostname helper method. This method extracts the hostname from a given URL by splitting the string at slashes and accessing the third element, which corresponds to the domain name. For instance, if the URL is http://example.com/path, splitting it by / results in http example.com path, and the hostname is simply example.com. This method ensures that we can consistently identify the domain of any URL, which is crucial for ensuring the crawler stays within the same domain during traversal. By isolating this logic into a separate method, the code remains modular and easier to maintain. Here, we begin the Java implementation of the web crawler. The goal is to traverse all URLs starting from the given start URL, but only within the same hostname. First, we define our crawl method, which accepts the start URL and an HTML parser instance as arguments. To handle the logic, we extract the hostname from the start URL using a helper method called getHostname. This hostname acts as a filter to ensure we only crawl URLs within the same domain. Next, we initialize a set called visited to keep track of URLs we've already processed, preventing redundant visits. A queue is also set up for breadth-first search traversal, where we begin by adding the start URL to both the visited set and the queue. The main loop processes URLs in the queue one by one. For each URL, we retrieve all the links on that page using the getURLs method provided by the HTML parser interface. As we inspect each link, we check two conditions: whether it has been visited already and whether it belongs to the same hostname. If both conditions are satisfied, we add the URL to the visited set and enqueue it for further exploration. Once a new URL passes the checks, it's added to the queue for subsequent processing. This ensures that all eligible URLs are eventually visited as the breadth-first search expands. When the queue is empty, meaning there are no more URLs to process, the traversal is complete. At this point, the visited set contains all the URLs within the same hostname that were reachable from the start URL. We then convert this set to a list and return it as the result. Finally, we define the getHostName helper method, which extracts the hostname from a URL by splitting the string its slashes and selecting the appropriate segment. This method is key to ensuring that we only crawl URLs belonging to the same domain. Additionally, the HTML parser interface is defined as specified in the problem, providing the getURLs method to fetch links from a given URL. With this implementation, the web crawler efficiently handles the domain filtering and breadth-first search traversal required by the problem. To solve the web crawler problem, we start with a simple example involving 3 pages. The input specifies the start URL as http://example.com/start. The HTML parser.getURLs method simulates the links found on each page. For http://example.com/start, it returns 2 links, http://example.com/about and http://example.com/contact. For http://example.com/about, it returns a single link, which is back to the start page, and for http://example.com/contact, it returns no links. Now, the first step is to extract the hostname from the start URL, giving us example.com. We then initialize our visited set with the start URL to track pages we've already processed, and our queue starts with the start URL as well. The algorithm processes pages in the queue one by one. First, we dequeue http://example.com/start, retrieve its links, and add any unvisited URLs with the same hostname to both the visited set and the queue. This results in adding http://example.com/about and http://example.com/contact to visited in the queue. Next, we dequeue http://example.com/about, process its links, and skip the start URL link since it's already visited. At this point, there are no changes to either visited or the queue. Continuing with the example, we now dequeue http://example.com/contact from the queue. Since the HTML parser.getURLs method returns an empty list of links for this URL, there are no further updates to the visited set or the queue. At this stage, the queue becomes empty, signaling the end of the crawling process. The algorithm then returns the list of visited URLs, which are http://example.com/start, http://example.com/about, and http://example.com/contact. This demonstrates how the algorithm effectively crawls all pages within the same domain while avoiding duplicates. Now, let's consider a more complex scenario involving cross-domain links. In the cross-domain example, the start URL is http://example.com/start, and HTML parser.getURLs for this page returns 2 links, http://example.com/about and http://other.com/page. The key difference here is that one of these links points to a different domain. As before, we begin by extracting the hostname, example.com, and initializing the visited set in the queue with the start URL. When processing http://example.com/start, we add http://example.com/about to visited in the queue because it matches the hostname. However, we skip http://other.com/page since it belongs to a different domain. After this step, the visited set contains http://example.com/start and http://example.com/about, and the queue contains only http://example.com/about. Next, we dequeue and process http://example.com/about, but since it has no outgoing links, the queue becomes empty. At the end of this example, the algorithm returns a list of visited URLs, http://example.com/start and http://example.com/about, showing how cross-domain links are ignored. Finally, let's examine an example with cyclic links, where pages link back to each other. The start URL is http://example.com/start, and it links to http://example.com/about. In turn, http://example.com/about links back to http://example.com/start. As usual, we extract the hostname, example.com, and initialize the visited set with the start URL and the queue with the same URL. First, we dequeue http://example.com/start and retrieve its links. Since http://example.com/about matches the hostname and hasn't been visited yet, we add it to visited in the queue. Now, the visited set contains http://example.com/start and http://example.com/about, and the queue contains http://example.com/about. Next, we dequeue http://example.com/about, process its links, and see that it links back to http://example.com/start. However, because this URL is already in the visited set, we skip it. With no further links to process, the queue becomes empty, and the algorithm concludes. The result is a list of visited URLs, http://example.com/start and http://example.com/about. This example demonstrates how the algorithm effectively handles cycles by tracking visited pages. The time complexity of the crawl function can be broken down into three main steps. First, we have the breadth-first search traversal, or BFS. In this step, the algorithm processes each URL exactly once, thanks to the use of a visited set that prevents revisiting. If there are n unique URLs within the same hostname, this traversal will iterate n times. Next, for each URL, we call html_parser.getURLs, which retrieves all the links on that page. Assuming there are at most m links per page, and with n pages in total, the total number of calls to getURLs is proportional to n*m. Lastly, each URL requires a hostname extraction using the get_hostname function. This operation involves splitting the URL string, which has a complexity of O(k), where k is the average length of a URL. Since this is performed once for each of the n URLs, its total cost is O(n*k). Combining the contributions from these steps gives us the overall time complexity of the crawl function. In the best, average, and worst-case scenarios, the time complexity is O(n*m plus k). Now, let's examine the space complexity, which is determined by the data structures used during the traversal. First, the visited set stores all unique URLs, and in the worst case, it holds all n URLs. Since each URL has an average length of k, this contributes O(n*k) to the space complexity. Additionally, the BFS queue can also hold up to n URLs in the worst case, contributing another O(n*k). Finally, there is auxiliary space used for the output of getURLs. Each call to getURLs may return up to m URLs, and since these URLs are processed one at a time without intermediate storage, this adds O(m*k) to the space complexity. When we combine these factors, the total space complexity is O(n*k) plus m*k in all scenarios. To better understand the efficiency of the optimized approach, let's compare it to a brute force method. In a naive approach, all URLs are visited without checking the hostname or maintaining a visited set. This would result in redundant visits and unnecessary processing, leading to a time complexity of O(total_URLs*m, where total_URLs includes URLs from all hostnames. The space complexity in this case would also scale with total_URLs due to the lack of filtering. In contrast, the optimized solution focuses only on URLs from the same hostname, avoiding redundant processing by using a visited set. This ensures that only n relevant URLs are handled, with efficient BFS traversal further reducing memory overhead. As a result, both time and space complexity are directly proportional to the number of relevant URLs, n, and their outgoing links, m. This makes the optimized approach highly suitable for large-scale web crawling within a single domain. One of the most common mistakes when implementing a web crawler is not filtering URLs by their hostname. If you don't restrict the crawler to URLs that share the same hostname as the starting page, it can end up crawling external websites. This not only violates the problem's constraints but also wastes resources and risks hitting rate limits. Another frequent error is failing to track visited URLs, which can lead to revisiting the same pages repeatedly. This is particularly problematic in the presence of cyclic links, as it can result in infinite recursion or unnecessary processing, significantly reducing performance. Additionally, ignoring edge cases with URL formatting, such as differences in trailing slashes or capitalization, can cause redundant visits to the same resource. Normalization ensures these subtle differences are addressed. Lastly, assuming all URLs are valid without validation or sanitization can lead to runtime errors when encountering malformed links. This highlights the importance of handling invalid inputs gracefully to avoid crashes. Another point to consider is overlooking parallel processing. If the problem allows for parallel crawling, relying solely on a single-threaded approach can significantly slow down the runtime. By not leveraging parallelism, you miss out on an opportunity to optimize performance, especially in real-world scenarios. Now, let's touch on some key interview insights. Always make an effort to understand the constraints of the problem. For example, clarify whether the crawling should be restricted to a specific domain or if there are limitations like rate limits. It's also important to demonstrate efficiency in your solution. Highlight strategies like URL normalization, deduplication, and multi-threading, as these show a deeper understanding of optimization techniques. Additionally, when choosing between BFS and DFS, justify your decision. BFS is often preferred for web crawling because it processes URLs level by level, which mirrors how users typically navigate websites. Finally, be prepared for edge cases during interviews, such as handling empty pages, pages with no links, or circular references. Addressing these proactively shows thoroughness in your approach. Web crawling problems are closely related to other graph traversal challenges, and understanding these connections can help deepen your problem-solving skills. For instance, LeetCode 269, the alien dictionary problem, involves graph traversal with topological sorting, which is a useful concept to know when working with directed graphs. Similarly, LeetCode 323, which focuses on counting the number of connected components in an undirected graph, shares similarities with exploring website structures. Another related problem is LeetCode 547, which also involves connected components but in the context of provinces, emphasizing graph traversal techniques. While not directly related to web crawling, problems like LeetCode 1249, minimum remove to make valid parentheses, can sharpen your skills in string processing and handling invalid cases, which are often necessary when dealing with malformed links or data during crawling. When designing your web crawler, it's important to assess different algorithmic approaches and their trade-offs. For example, depth-first search, or DFS, uses a stack or recursion to explore deeper into the link structure. While it has lower memory requirements, it may not be ideal for wide structures like the web. On the other hand, breadth-first search, or BFS, processes URLs level by level, making it more suitable for web crawling as it mirrors how users navigate. However, BFS typically requires more memory to maintain the queue. Multi-threaded crawling represents another powerful approach, as it can significantly speed up the process. However, it also introduces complexity, such as ensuring thread safety and managing shared resources. For large-scale crawling tasks, distributed crawling can be an effective solution. By distributing the workload across multiple machines, you can handle vast datasets efficiently. However, the setup and orchestration involved add significant overhead, so it's important to weigh these factors based on the problem's requirements. Thank you for watching. To wrap up, we explored the web crawler problem, discussed the brute force approach, and reflected on its real-world applications. Remember, mastering graph traversal techniques like BFS and DFS will be invaluable for similar challenges. Don't forget to like and subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!